But the MCAT is a lot more problem solving. It's a lot more puzzling. And so the MCAT is throwing stuff at you that they know you haven't seen before. They know that this is all Greek to you.
Phil, back for some more MCAT podcasts. How are you doing today?
Good. Glad to be back.
I'm excited to jump in, continue on our path of Blueprint MCAT, formerly Next Step Test Prep Blueprint MCAT Full Length 1, which everyone can get for free. Passage 9 we're on now. Chem Phys.
Yeah. We're nearing the end of the Chem Phys section.
Yeah.
We're in the short rows, as my dad would say. He's a farmer, so.
How many passages are in each section? Or in the science and psych soc?
That's a loaded question. Depending, are we talking COVID world or are we talking
non-COVID
normal world? So normal, non-COVID world, we're dealing with 10 passages on test day. In the COVID world, -1. But so I think we have 2 passages left and still one last discrete section.
Nice. All right. So coming down the home stretch.
Yeah, the short rows.
The short rows, yes, as they say. All right, let's go ahead and jump in.
All right. So just kind of like start off. So a prodrug must undergo chemical conversion in the body before becoming an active pharmacological agent. The metabolism can occur in the stomach before absorption takes place in the blood or even in the target tissue. The prodrug, macetalmerade, I think that's how you pronounce it.
Sure.
Close enough. Is absorbed in the duodenum and then undergoes acid-catalyzed hydrolysis of its acetyl functional group to become an active metabolite. So looking at this, they're definitely, giving a lot of background info here about just like, activating a drug. A lot of times we have to metabolize them. Not a lot of stuff that I think is super testable. I expect to see questions on. It's just a lot of background info. And then, they do talk about this specific drug. And so there's probably going to be some more questions coming on about it. But first paragraph, a lot of background stuff. Don't want to get bogged down. So the para-substituents on the aromatics can influence the relative stability of the carbocation intermediates and impact the rate of acetal hydrolysis and macetalmerade efficacy. To investigate the role of para-substitution on the stability of this carbocation intermediate, chemists use isodesmic reactions to determine the relative stabilization energy for various substituents. Isodesmic reactions, I'm really glad that they're giving us a definition of this because that's probably a new term for most test takers, are reactions in which the type of bond broken in the reactant is identical to the type of bond formed in the product. So this relative stabilization energy provides a means of measuring the difference in the energy needed to form the cation as a result of the presence of the given substituent as shown in Figure 1. Figure 1 shows the isodesmic reactions involving macetalmerade carbocation used to calculate the relative stabilization energy for a substituent labeled X. Whew.
Wow. All right.
We're back in the Chem Phys.
I'd be skipping this section, this passage.
Yeah, definitely kind of a tricky passage. This paragraph goes real deep, real quick.
Yep.
Basically, they're telling us that we have these reactions, and we're trying to figure out, switching these different groups on the para side of our aromatic ring, which is just a fancy way to say the opposite side. On the complete 180 degree on the ring. So switching that out for different things, how stable will it make this? Will it stabilize the reaction? So we're calculating these relative stabilization energies by switching out these different substituents. And so in equation 1, this figure, they give us this with like some X thing. And then we are pulling a hydrogen off of that version with the X and adding it to the other compound. And so we're able to do this, calculate the heat released or absorbed, and that tells us something about how stable a product is. If it's really stable, then it's going to release a lot of energy. And if it's really unstable, then we're going to have to put a lot of energy into it to get it there. But yeah, a lot of background info. It's very easy to get kind of like glazed over in that paragraph. I expect to maybe see some questions about this relative stabilization energy and maybe something about this isodesmic reaction. The MCAT writers know that you haven't seen that before, and so there's a good chance they might ask a question about it.
Okay.
So moving on, passage still isn't over. We have a chemist evaluated the effects of 5 different substituents at position X. For each compound, the heat of formation was calculated for the substituted neutral compound and cation, X and X plus respectively, along with non-substituted neutral compound and cation, H and H plus respectively. The change in heat of formation from H to H plus and X to X plus gives the energy required to deprotonate each compound, and the difference gives the relative stabilization energy. What are you thinking? A little bit of a throwback to Kim, for sure. This figure, luckily, I feel like kind of helps. Talking about the change in energy as we go from H plus to H, and then X to X plus, because looking back at equation 1, note that we have the molecule on the left is losing a hydrogen, that's going X to X plus. The molecule on the right is going H plus to H. And so if we look at the relationships between those, we can figure out overall, is this going to be more or less stable? And figure 1 helps us in conjunction with equation 1 to understand like the energy just being transferred back and forth between the two forms. So the heat of formation, the energy required to deprotonate, and the relative stabilization energy was calculated for each compound and recorded in table 1. And then they give us this table. Now, just like some background info, I expect that we're probably going to have most of our questions about this table 1, because table 1 is where we actually have the data. Like everything up until now has just been explaining like how to set this stuff up. And then in table 1, we actually have some actual numbers and data. And so most of our questions are probably going to be focused in on this specifically. Taking a moment to just like address this table. This is something the MCAT does that very often, try to turn up the difficulty on passages, which I feel like is no surprise to people looking at this passage. But as I look at this table, we have compound 1, 2, 3, 4, 5, and we have different X components. So up in the equation 1, we have like X on these rings. And so these are just the different X groups. So we have like our ether, a methyl group, a hydrogen, a fluorine, and an NO2. But then if we look at like the next 3 columns, those are all exactly the same.
Yep.
And so none of those need to be there. I feel like those are just added there to make this passage a little bit more complex.
To slow you down.
Yeah, slow you down, make it a little bit more difficult. As I glance at it, like all of those are the same. So I know they're not going to ask me a question about that. So I don't really care much about those things overall. Versus you go on a little bit farther and you see like HF for the X version and the X plus and the change in energy as we go from X to X plus. And so as I look at these, hopefully, like because I know I'm going to see a lot of questions, I'm actually going to spend a little bit of time kind of glancing at these values because I know that there's going to be some questions built around these. And it turns out the predominant portion of the questions here are going to be based off of this. And so as we look at this, we note that, hopefully we note that there's kind of an odd one out in that table.
The NO2.
Like the one with, the NO2. So if we look at the heat of formation of this, and the energy from like becoming the ionized spores, that like second to last column, the HF is going to release energy. The other ones are all going to take energy, with the fluorine requiring the most amount of energy. And then we have the relative stabilization energy, and we can see that the NO2 is going to make it real stable, and the other ones maybe not quite as stable. So there we go for the
how
passage.
Can someone so the first question that I have looking at this table, and again, if you're listening to this on a podcast, go watch on our YouTube channel where we have the video of this. The negative versus positive. How do I just interpret that quickly? That's the first thing that pops into my mind.
Yeah. So this also helps to kind of like look up at the figure 1 up above. And so we can see what happens as we go from X to X plus. And if that's going up, that means we're going from a lower energy to a higher energy. So that means it's going to be an endothermic reaction because we're going from a lower energy thing to a higher energy thing, and energy can't be created or destroyed. So we must be absorbing energy from something or putting energy in. And so a positive H is going to mean that we're putting energy into this. A negative is going to mean that we're releasing energy.
Okay.
Because then we would be going in the opposite direction.
Okay. So in this figure 1, the H plus to the H would be a negative number, potentially an X to X plus positive number.
Right.
Okay.
Right. Yep.
Okay.
Yep. So we got some questions.
Yeah.
Yeah. So looking at question 48, which of the following cations would form most quickly from the loss of a hydrogen atom? What are your thoughts?
Go ahead and read the answers here.
So we have the different forms of this. This molecule with the X on it. We have the one with the ether. We have the one with the methyl group. We have the one with the fluorine and the one with the hydrogen. So we have all of these different X groups. And technically, these would be the X plus. Yeah. So we're trying to see which of these would form the most easily or most quickly the X plus.
And so the most quickly potentially, so we have to look at the graph and go, okay, which one of these numbers is biggest or smallest? So that's the first thing. So if we look,
it's got to be one of the extremes. So right off the bat, you should be able to get to a 50-50.
Yep.
Because they're asking about forming a cation.
Yep.
That means we're going to be looking at the column that's the delta H for the X becoming an X plus. So like forming the cation from just kind of the natural form. So it'd be the second to last column.
Yeah. And so they're all relatively close to each other. Again, the question, so starting off with the, is that the methyl group?
The OCH, be like ether.
The ether, yeah. So that's 181.8, and the fluorine is 191. So do I go for highest? Do I go for lowest? So the energy, the delta H, the quickest, I'm assuming the delta, the one that requires the least is going to go faster. So the 181.
Right. So the ether group requires 180 joules. The fluorine is going to take 190. Everything else is in between.
Yep.
So the one that requires the least amount of energy is going to be the fastest. I would have chosen the NO2, except for that wasn't an answer choice. Like that one's going to form real quick because that gives off energy. That wants to go forward.
Yeah.
But of the answer choices, the ether, the CH3O is going to be the one that I'm going to go with.
Nice. All right. 1 for 1. All right, question 49. What is the correct order of the 5 para substitutes on the carbocation intermediate if arranged from most stabilizing to least stabilizing? On the carbocation intermediate. So I'm lost with the definition of that, the carbocation intermediate.
Yeah, so we're looking for like the order. We're trying to put these things in order of like most stable to least stable.
Yep.
Right. And they're looking for the carbocation intermediate. So I think they're looking for like the X plus sort of thing. But because they're talking about the stabilizing, right? Like that should be like scratching this itch or ringing this bell in the back of your brain where you're like, wait a minute. That was the last column where they talked about relative stabilization energy. That whole column is just about stabilization.
Yeah.
And so they're asking us to put those in order from the most to the least stabilizing.
Yeah. From the most to the least. And so most stabilizing, I'm assuming, is that NO2 at negative 260.
Yeah, that thing's super stable.
Yeah. And so that gives A and B are out. And these answer choices are way too long to read off for the podcast. So again, go watch the YouTube video. Answer choices C and D both have NO2 as the first one. And so we're down to 50-50. The next one, we would go to negative 6.3 because that's the next highest one. That's OCH3. So answer choice C should be the answer without looking at anything else.
Yeah, exactly. No, we need to start at the NO2 and end at the fluorine, so C is the only viable answer.
Mm.
Yeah.
Cool. I like ones where you can just quick step, go right to it.
Yeah, this passage is very complex as you're reading it. Like I know most students, when they get into that second paragraph, their like brain is probably going to shut down and they're going to kind of glaze over a little bit. But like most of this turns out to be just like interpreting this table, being able to apply that. So like luckily, like making sure that you're looking at the right place. They're asking about the stabilization energy, so I'm going to look at the stabilization energy one, and being able to pull that out. So question 50, the next question here. During the experiment, scientists noted that several of the reaction beakers became hot to the touch. All the following reactions could cause this result, except. So we have a bunch of different reactions here. Looks like we're forming these like X things out of the other one. The top one looks like it's the ether one. Then we have the fluorine, the methyl, and then the NO2 as answer choice D.
So obviously exothermic, right? So which ones are giving off energy, or the question here is which one isn't giving off energy? So looking at the fluorine one, so it's a game of which one of these is not like the other. Should we be looking at the RSE or the delta H for the X plus?
Yeah, I'll probably do like delta H for the X plus is probably what I'm going to look at, because we're like crafting this, forming it out of ingredients.
Okay. So looking at the delta H for X plus, all of them are hugely positive except for the NO2. And so I'm going to choose D, which is the NO2 at the end, but I don't know. That's just because it's the one that doesn't look like the others.
Yeah, it's the odd one out.
Yeah.
And that's exactly what I encourage my students to do whenever we see this question. Like the question saying like all of these become hot except for one of them. And so we know 3 of them do one thing, one of them does something else. As we look at our table here, in the HF, the heat of formation for just the X, the NO2 is different. The next column, NO2 is different. The next column, NO2 is different. So it's kind of like it's the one that's not like the others. And so I'm just going to pick that one and move on. And I'm not going to overthink this on test day, because that's the odd one out.
Yeah.
Yeah.
I mean, even if you were to look at the RSE column, again, it's the odd one out. The delta H, odd one out. The HF for X plus, odd one out. So you hopefully would have gotten that one right, no matter what column you looked in.
Yeah. And so that's also something, like I said, a lot of students read that second paragraph and are just going to immediately shut down. And they're going to be like, done. And so people are going to come to this question. Those people are going to come to this question and immediately just be like, I don't know, throw up their hands and then move on.
Yep.
But like with any amount of like effort on this, like, it doesn't really even matter what column you look at. Like, you notice that the NO2 is the weird one. And so that's, some motivation to like, don't just throw up your hands in the air if you feel a little bit lost. You could completely like misunderstand what's going on here with this like stabilization energy and still be able to get a majority of these questions. But just kind of like using some educated guesses, kind of like gaming the system. It's the application side of things rather than just straight up knowledge that the MCAT's trying to test with this data interpretation stuff.
Yeah. Whew. All right. Yeah, it seems like the more that I dig into this whole MCAT thing, and especially in the cars section, it seems like and getting feedback from students on how these podcasts have really helped them, it seems like those who really make the biggest shifts are the ones who don't give up and are just like, this is just here to confuse me and piss me off and make me doubt myself, but I'm just going to keep pushing forward and have confidence that I'm going to be able to figure it out.
Yeah, absolutely. I think that's something that a lot of students have trouble with in undergrad, because in order to do well on a test, you have to like memorize this material. You show up on test day, you show them that you know the material, and then you're fine. But the MCAT is a lot more problem solving. It's a lot more puzzling. And so the MCAT is throwing stuff at you that they know you haven't seen before. They know that this is all Greek to you.
Yeah. And
they're just trying to see how well can you like keep going and, just try to figure out what you can figure out from the passages themselves. Yeah. That's honestly one of the reasons I like the MCAT so much. It's kind of like a puzzle, where I was like, I get to figure out all these like weird things as I go along.
Yeah. Good job with that. All right. Question 51. What effect will the addition of a fluorine substitute have on carbocation stability? A, the fluorine group will be destabilizing because it is highly electronegative. B, the fluorine group will be stabilizing because it is highly electronegative. So those two are opposite. C, the fluorine group will be destabilizing because it has additional lone pair electrons. And D, the fluorine group will be stabilizing because it has additional lone pair electrons. All right, so A, B, and C, D are both opposite of each other. So we add fluorine on the carbocation stability. And again, we know that the fluorine here was the highest for that delta H for X to X plus. If you add fluorine, I don't know. The electronegative, the lone pair electrons. Obviously, the periodic table potentially may have to look at that to see for lone pair electrons where fluorine is. I don't know how to do this one.
Yeah, it's definitely a little bit tricky. One thing I would kind of like start with is like we knew that the NO2 like that's going to make this like way more stable. And the fluorine was on the opposite end of that spectrum, right? So if anything, the fluorine is going to make it less stable. And so that in and of itself means I probably want to lean towards A or C.
Okay.
Because those are saying it's destabilizing. It's not making this more stable.
Yeah.
B and D are both saying it's making it more stable. Now, if there's anything that any MCAT student knows about fluorine, it's probably that it's electronegative. It's the most electronegative. That's like fluorine's like claim to fame. And so like I kind of want to go with A just off of that. Now C is also true though. Like it does have a lone pair of electrons. However, so does the oxygen in that ether, and that was stabilizing. And so I don't want to say that it's destabilizing just because it has lone pairs of electrons, because there's other ones that have lone pairs of electrons and they're not destabilizing. The nitrogen also has or can have a lone pair with a resonance structure. So off of that, I know like fluorine's really electronegative. I also know it's destabilizing because it's like one of the main ones here that raises the energy, and so it makes it less stable. So A is going to be the one I want to go to with that.
Okay, so just the destabilizing right off the bat because it's the opposite of that NO2, which we know is stabilizing, and then which one is more true?
Yeah, also looking at the heat of formation, right? We talked about how it's like such a big number for fluorine, so that required a lot more energy being input into this one, and so that means it's not going to be as stable. Higher energy is the same thing as unstable.
Okay.
In chemistry.
Okie dokie.
All right, I think we got our last question here, question 52. The reaction to produce the X form of compounds 1 through 4 from the standard state elements will be spontaneous under what conditions?
Go ahead and read those questions there, the answers.
Yeah, so the reaction will be spontaneous under all conditions. The reaction will be spontaneous at high temperatures. The reaction will be spontaneous at low temperatures. And the reaction will not be spontaneous under any conditions.
So, we know from the chart that delta H for XX plus, or actually to produce the X form, which is opposite of X plus, right?
Right. So that'll be just be that the HF or just the X.
Yeah. So the HF for X. All right. So negative, 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 and then the NO2 is positive. So negative is more stabilizing, right?
Yeah. So it's going to release energy.
Yeah.
As we form those.
Yeah. But does that also mean more wanting to go that way?
Yeah, and so the heat of formation, this is releasing energy. So the products are going to be more stable than the reactants are going to be.
Yep.
There's kind of like two sides of things that kind of determines whether a reaction wants to become spontaneous. One, every reaction wants to become more stable. Things want to go from less stable to more stable.
Yep.
The other thing is that stuff wants to break down. Like if you have like, a pile of Legos and you put it in a bag and then you wiggle the bag around, it's very unlikely that you're going to pull out a castle, right? Versus if you put a castle in a bag and you wiggle it around, like you're going to get a bunch of like individual Legos. So stuff wants to break down. That's the push for entropy As reactions go by, we expect things to kind of like break down more than become more complex. And we also want things that are going to release energy. So looking at this like spontaneity, we're dealing with Gibbs free energy, which is the delta G. If that's a negative number, that means it's spontaneous. If it's a positive number, that means it's non-spontaneous. And so we can kind of figure this out based on the equation delta G, or the Gibbs free energy, is equal to delta H, the heat of formation, minus the temperature times the change in entropy or disorder, the T delta S. And so the question is asking about reactions or like compounds 1 through 4. And so as we look at that, the heat of formation for all those is negative. So our H is negative in all those cases. It doesn't really matter what the number is because they're not asking us for a calculation here.
Yep.
So that's going to be negative. So if we're doing heat of formation, that means we're forming this from all the elements. That seems not very likely to occur in spontaneity. And so if we look at our entropy, our disorder, which is what S is, our entropy is going to be, if we're like forming this out of its individual substituents, the disorder is decreasing. So we have a loss in disorder as we're building these molecules out of their ingredients overall. And so our delta S is also going to be negative. Now, because our equation for Gibbs free energy is delta G is equal to delta H minus T delta S, our S is negative and our H is negative. Now, because it's H minus T delta S, the minus T delta S, because the S is negative, that just becomes like positive because it's minus a negative. So we end up with a negative number plus some like temperature times another number. And so if we want a negative delta G, which is what we're going to have for spontaneity, we need our temperature to be a small number because we're going to have like some negative number plus temperature. And so if the temperature is big, then it's going to be a positive number. If the temperature is small, it's going to be a negative number. So we want negative for a spontaneous reaction. So I'm going to go with C here. The reaction is going to be spontaneous specifically at low temperatures. So this question is actually, I think, a little bit more complex than some of the other ones that we've seen up until now. The other ones require you to just kind of like interpret the table. And so like even if you're like a little bit lost, you can like figure out like, oh, like which one of these is the odd one out. This question is requires you to know some things about like entropy and like enthalpy and Gibbs free energy. You got to have this equation. You got to be able to kind of manipulate that. So even though you have to know the equation, it's not really like a math heavy thing, right? Like you're not taking the square root of 17 or anything like that.
Yeah.
You just need to know like, positive, negatives, how do these things interact with each other? But you also need to be able to interpret the passage and the data. And so I think because this requires some outside knowledge being applied to the data and the passage and, applying it to the entropy and enthalpy stuff, it's going to make this question a little bit trickier.
Would there be, to help students kind of cross out some of these, would there be any situation where reactions will never be spontaneous ever?
Yeah. So like if something is like requires a lot of energy to be put in and it's becoming more ordered, like that doesn't ever really want to happen because two things want to happen. We want to like be lower energy and we want to be and we want to break down things. And so as this reaction is going forward, it is becoming lower energy because that delta H is negative. So it's becoming more stable, but we're also like organizing because we're going from like individual small things to large things. So because we have two things pushing in opposite directions, like as we release energy, that's stabilizing, we're building something that's destabilizing. That means we're going to have some scenario where like sometimes it works and sometimes it doesn't. So just off of that, I probably want to go with like B or C because like that's something that kind of like fits through there. In order for something to be spontaneous under all conditions, we need it to like release energy and be like breaking down. In order for it to be not spontaneous under any conditions, we need it to be like becoming higher energy and becoming like a more organized, complex stuff. Because that's not really favored under any conditions in the universe.
Okay. Wow, that was a hard passage. So again, going back to my comment earlier about it just seems like students who are reaching out, who are becoming more successful because of these podcasts, they're the ones that just push through and don't glaze over and just understand that maybe you're not supposed to understand everything that you're reading, but just get through it and go back as you need it.
And I think that's by design. Because the same thing's going to happen as a physician. Like, you don't always expect everything. Maybe the patient comes in, says their back hurts, and they lift up their shirt, and you're like, oh my gosh, like there's a 2x4 sticking out of them or something. And so you need to be able to kind of assess, like, okay, what do I know? What can I do? And that's something that comes in on the MCAT, as well as being a physician, obviously.
Yeah. All right, another one in the books.